So let's continue with this. Ethan, can you hear me?
Yep.
Okay. So we were actually doing this past paper last time as well, and we have to continue completing this past paper. So it's we're going to start with question. These were the questions that we had already done. It was a 9701. It's summer 17 question paper 1 2. Uh, Now we're going to start with question 21, which is that geraniol and let me just open a board link on the side. Okay, so the question is that there are two molecules given over here, and he's saying which statement about them is correct. So the first one is they're chain isomers of each other. Now, chain isomers are the ones where you have, I mean, the chain is different. Over here, the chain is exactly, I think it's exactly the same. Like it's the same carbon atoms connected in exactly, and the branches coming out in exactly the same manner as in the other one. So it's not it's probably not a chain isomer because everything, I mean, the chain looks exactly the same, the carbon chain. The next one is they're geometrical isomers of each other. They're not. So they're not geometrical isomers because in geometrical isomers the structural formulas are exactly the same. In stereoisomers, the molecules look exactly the same, except I mean they're bonded in exactly the same way. Over here, they're not bonded in exactly the same way. For example, there's an OH over here. The OH over here is at a different position. So B and C are definitely not correct because for geometrical and optical isomers, for stereoisomers, the structural formula has to be exactly the same. Only the three-dimensional arrangement is different. The last one is the one that's left, and therefore they're going to be positional isomers. Why? Because you can see that the position of the bonds and the position of OH groups, that is different. For example, the double bond is over here, and over here the double bond is at the end. The OH group position has also changed. In the other one, the functional group position is at some other place. So they are position isomers.
Said they're not geometrical and optical isomers only because the OH group has been exchanged for the position. Yeah?
Huh, but remember, for stereoisomers, everything has to be exactly the same. For example, if you have an optical isomer, okay, let's say this molecule has a chiral center, okay. So this one is going to have two optical isomers. The structure would be exactly the same. Ibrahim, do you get the point? It's only that the three-dimensional arrangement is going to be different. That the first one, I mean, this carbon atom is chiral, so the three-dimensional arrangement would be there would be two three-dimensional arrangements, and there would be mirror images of each other. Ibrahim, do you get the point?
Yes, Ajay.
Okay. And similarly, even in geometrical isomers, uh, the three-dimensional arrangement is the one that's different. Like if you draw the structural formula of this molecule, it's going to be CHCl, and there's going to be a double bond, and then there's going to be another CHCl. Uh, the structural formula would be exactly the same. I mean, the atoms would be bonded to the same. I mean, the connectivity would be exactly the same. It's only when you draw the three-dimensional structure that's going to be different. So since the structure is completely different, like double bond positions at the end, they're completely different. So they can't be stereoisomers. Next one is which equation represents the initiation step in the substitution reaction between methane. So this is the free radical substitution, and if we can go over free radical substitution, if we can find this is halogenoalkanes. 1 second. So probably over here, this was the first reaction that we did. It had 3 steps. I mean, this is all about naming. Yes, this one. So it had 3 steps. The first one was the one where free radicals were produced. That was the initiation step. Due to UV light, free radicals were formed. Cl radicals were formed, and then those Cl radicals started pulling hydrogens away from the hydrocarbon or the carbon chain, and the Cl became HCl. The carbon chain became a radical now because its hydrogen is gone, and then it would attack a Cl2 molecule to get back its bond or an electron from the Cl atom and would bond with it. So this was propagation then. So the answer to this question is C. That's the first step, initiation. Next one is you have aqueous sodium hydroxide and reacts with 1-bromopropane to give propan 1-ol. This is a halogenoalkane reaction. Remember, it's 1-bromopropane. 1-bromopropane. Propane is 3 carbon atoms. 1-bromo means that bromine is on the first carbon atom, which makes it a primary halogenoalkane. So it's a primary halogeno. It's a primary halogenoalkane. And what happens in primary halogenoalkanes, that they have 3 nucleophilic substitution reactions, which are shown over here. He's talking about a reaction with NaOH. The halogen is going to get substituted by OH. But since it's a primary halogenoalkane, the mechanism that would be followed would be the Sn2 mechanism, where the OH ions are going to attack. And let me just confirm whether it's NaOH aqueous. Okay, it is aqueous NaOH. So what's going to happen is that the OH ions are going to attack the carbon, and a transition state would be formed where the OH would be getting bonded to the carbon atom, and the Cl would be getting repelled, and then the Cl would break off. So what should be included in a diagram of the first step in the mechanism? Should be included in a diagram of the first step in the mechanism. A curly arrow from a lone pair on the OH to the carbon positive atom. I think this makes perfect sense. Because there's a curly arrow, OH -1, it has lone pairs, it's a nucleophile. The lone pairs are going to be attracted to the carbon, which is partial positive. And the electrons on the other side are going to get repelled. So that is what's going to happen in the first step. But we can, just to be sure, we can look at all the other steps as well. A curly arrow from the carbon positive, that's incorrect. Remember, arrows represent the movement of electrons. The electrons are coming from the OH ion and they're moving to the carbon positive. So the arrow or the curly arrows, they always represent the movement of electrons. A curly arrow from the CBr bond to the C atom. It's not CBr bond to the C atom. It's actually, if there's a CBr, the electrons are moving towards the Br. So that's also incorrect. And homolytic fission, this is not homolytic fission. It's heterolytic fission. The bond is breaking unequally. The electrons in the bond are moving towards one atom. They're not getting distributed equally, like half. It's not equal bond breaking. It's equal bond breaking is homolytic fission. If the electrons are unequally divided, then that's heterolytic fission. So homolytic fission is also incorrect. Now, next one is a sample of 2.76 grams of ethanol was mixed with an excess of aqueous potassium dichromate 6, which means he's oxidizing the ethanol. And the reaction was boiled under reflux for 1 hour. That means the reaction is going towards completion. Now, ethanol is a primary alcohol. So ethanol is a primary alcohol, and that, one second. So ethanol is a primary alcohol, and primary alcohols would turn into aldehydes. And then those aldehydes would turn into carboxylic acids. Okay, so that's the oxidation of primary alcohol. But since he's boiling it for 1 hour, that means the end product is going to be a carboxylic acid. So it doesn't matter that at the end of the day, he's collecting the product by distillation. Remember, aldehydes can only be formed if you distill right away. Like you you don't even reflux for 1 hour. I mean, if you're refluxing for 1 hour, that means this is going to be formed. There's no way there would be any aldehyde left. All of it is going to get oxidized. So it doesn't matter that you start distilling at the end, because all of it has already changed into carboxylic acid. The only way we discuss that aldehydes are going to be formed is when you don't use reflux. You immediately distill and you allow the aldehyde, because it doesn't form hydrogen bonds. It has low melting and boiling points. It evaporates very quickly and you collect it. So, anyways, this is the product, carboxylic acid. The yield of the product was 75%. What mass of product was collected? So we're going to find the moles of ethanol. It's going to be 2.76 grams divided by the MR of ethanol, which should be 46, I think. Two carbons, that's 24 plus it is 46. So mass over MR, that is going to give you moles. Can anyone tell me what the moles are?
0.0469.
So 0.0469 moles.
Make it 0.047.
Okay. And this one is also 0.047 moles, right? And multiplied by the MR to get the mass. The MR of this is 60. So what do you get?
2.82.
2.82.
82.
So you're getting 2.82 grams. And the yield is 75%, which means only 75% of the output is going to be obtained. So 75 over 100 into 2.82 grams is going to give you what?
2.11.
And we don't have that answer. So can we redo the calculations just a second? Just let's recheck. It's an ethanol molecule, and it's definitely going to change into a carboxylic acid molecule. Check the MRs. I think they are fine. Actually, it's not 2.16. Sorry, it's 2.76. I've copied it incorrectly. It's 2.76 grams. Okay, that's where the error is. So just quickly, 2.76. Divide that by 46.
D.
Okay, that gives you 0.06 moles. 0.06 moles should be multiplied by, it's D. Just
It's D.
0.06 should be multiplied by 60. That gives me 3.6 grams, and 75% of 3.6 grams should be, just 1 second, 3.6. It's going to give you 2.7, right? Okay, Bhaskar, you're getting the same answer, right?
Yes, sir.
Sir, why are we considering the moles of alcohol equal to the moles of acid? मतलब उसका MR तो different है.
One molecule is going to produce one molecule. Well, is it possible that one molecule is not going to produce one molecule or more than one molecule?
ठीक सही, all right.
Okay. As a next one, compound X is a single pure optical isomer. X is heated with an excess of concentrate sulfuric acid. Only one organic product is formed. So you're saying it's a single. So X is a single molecule. So that's the first statement. That is what is meant by the first statement. No optical isomerism is happening. It has a single pure optical isomer, and it's heated with an excess of concentrate sulfuric acid. Sulfuric acid is a dehydrating agent. So only one organic product is formed. Now, what happens is that when you dehydrate a molecule, the OH is lost, and I mean this carbon has two hydrogens, right? This carbon also has two hydrogens, and an H would be lost from the neighboring carbon atom. So, and there's going to be a double bond that's going to exist over here. So that's one possibility. The other possibility is that the double bond is formed on the other side, and the H is lost from this side. So that's your other possibility, that the double bond might exist over here. So both molecules would be different, because if the double bond is over here, the structure of the molecule is different. Okay, for example, if we rub this off, So if the double bond is over here and the OH is gone, the structure of the molecule is going to be different. The double bond would be very close to this carbon chain. And if the double bond is on the other side, then the structure of the molecule is different. It's further away from these carbon chains. And so it's basically two different molecules. So A can't be the answer. It's going to give you two different products. The same would happen over here. The OH would be lost and H would be lost from the neighboring carbon atom. So a double bond might form over here. So that's one molecule that you're going to obtain, or the double bond might form on the other side. So that's the other molecule that's going to be obtained. And the same would happen over here as well, that either the OH would be lost, a double bond would be formed over here. So that's one molecule, or it would be formed on the other side. So that would be the other molecule. Now in the last one, D is the answer. In the last one, there's an H on the neighboring carbon atom. So the OH would be lost, and then H would be lost from the neighboring carbon atom, and the double bond would always be formed over here. I mean, that's the only possibility. There are no options. I mean, the OH, the carbon over here, there's only one neighboring carbon. So it's not in the middle. The OH is not in the middle of the chain. It's right at the end. So there is only one neighboring carbon atom, and it only has one H. So the double bond would always be formed over here, and it's always going to give you just one molecule. Okay? Is this clear? Rida, Hiba, is this
Sir,
clear?
C में अगर आप देखें तो C में the carbon that is attached to OH group also has only मतलब one possibility. What is
Why?
the second possibility? क्योंकि मतलब this carbon is attached to four मतलब different groups.
I mean,
So it has no height.
It has three possibilities. The OH would be lost, the H would be lost from here. So क्या होगा? Double bond would be here, right?
जी.
And then there's a possibility that the OH would be lost and the H would be lost from this carbon atom. So the double bond would be formed over here. And
Alright.
there's actually a third possibility as well. Okay, there's another carbon chain which has, this carbon has 3 hydrogens, right?
जी sir.
So there's another possibility. The OH would be lost, the H would be lost, and a double bond would be formed over here.
ठीक
So
सही got it.
That's 3 different molecules that are possible. Okay. Next one is 2-bromo 2-methylpropane undergoes nucleophilic substitution when heated under reflux. So what is 2-bromo 2-methylpropane? So that's propane is 3 carbon atoms. 2-bromo means bromine is on the middle carbon atom. And 2-methyl means there's a carbon chain, 1 carbon on the middle carbon atom. Now this is a tertiary halogenoalkane, and tertiary halogenoalkanes, they undergo Sn1 mechanisms. What's the Sn1 mechanism? Primary halogenoalkanes undergo this mechanism. Tertiary halogenoalkane, the Cl is going to break off first, and then the OH minus 1 is going to be attracted to this carbocation. Because there's so many carbon chains, the carbocation is going to be more stable. The carbon over here is not going to have a very strong positive charge, which is why initially it's not going to attract the nucleophile, the OH minus 1, like it does in the primary halogenoalkane. So it's going to be Sn1 mechanism. The hydroxide ion is helped in its approach to the central carbon atom by the methyl groups. The intermediate carbocation, this is B is going to be the answer. Because what we talked about over here is, let me just revise this. Why was the mechanism different? The mechanism was different because over here the carbon had a much stronger partial positive charge. Why did it have a stronger partial positive charge? Because there weren't any large groups around it. They were just hydrogen atoms. The hydrogens don't have electrons. They just have 1 electron. So the positive charge is not surrounded by a lot of electrons or large groups or electron donating groups. Hydrogen barely has 1 electron. So the positive charge is a lot stronger. So it doesn't let the Cl go away. Cl is partial negative, but because of the stronger partial positive charge, the Cl would not, it would be very hard for the Cl to break away. But at the same time, because it's a very strong partial positive charge, it attracts the OH minus 1 directly. And the OH minus 1 is the one that comes in and pushes or knocks out, because of the negative charge on the OH ion, it pushes the Cl away. Because the Cl it was very hard to knock out the Cl away because of the strong positive charge. But over here, what happens is that when this Cl partial negative and the carbon is partial positive, when the Cl tries to take away electrons, this carbon is not going to pull the negative Cl back. Why? Because if the carbon gets a partial positive charge, it has very large groups around it, lots of electrons around it. Carbon chains have electron donating effect, which basically decrease the positive charge, and which is why it's not even going to attract the nucleophile in the first place. So the Cl can easily take away the electrons because there's nothing pulling it back. So which is why the first step of this reaction, the easiest step, is that the Cl takes away the electrons. And that was because of the inductive effect, the electron donating effect of the carbon chains. And the electron donating effect of the carbon chains would also make the positive charge on the carbocation a lot lesser. The charge density is going to be a lot lesser because lots of big groups are attached around it. So when the Cl breaks off, it's going to let it go. I mean, it's not going to pull it back because this carbocation, this carbon positive, can pull electrons from other places. There are lots of large groups around it. And if the OH ion concentration is sufficiently high, the OH ions would start coming in and would start joining in with this carbon atom. So, and we did talk about the stability of the carbocation somewhere. I don't know which board it was. But this statement, remember this statement, that the intermediate carbocation in an Sn1 mechanism is stabilized by the inductive effect or the electron donating effect of the methyl groups. Is this clear? Ethan, Mohammed, is this clear?
Yes.
Hamza?
Sir,
Okay.
I have a question.
Yeah.
Yeah, so what if the question would ask us, like for a secondary alcohol, which mechanism it undergoes? What should we write?
I told you secondary halogenoalkanes, they can have, it depends because the whole difference was, let me explain the difference just a bit. Where's the, I mean, the whole difference was that, I mean, this was the difference. Like if you have a carbocation, in primary carbocations are not formed. Reason being, the positive charge is kind of large. So it's not going to let the Cl -1 break off. Okay, so there's going to be a very strong attraction. It's not going to let the Cl -1 break off unless there's this OH -1 coming in, and that OH -1 is then pushing the Cl away. So that was, you had an unstable carbocation. So you had an unstable carbocation. Unstable meaning that it has a strong positive charge. Now in the tertiary halogenoalkanes, that particular carbocation was surrounded by very large groups. So if the Cl -1 breaks off, the carbon positive can pull electrons from other places. So it could pull electrons from other places, and the positive charge is going to be lesser. And it would allow the Cl -1 to leave. As now about secondary halogenoalkanes, it depends. Like they're somewhere in the middle. Now it depends. Sometimes they're going to follow Sn1, sometimes they're going to follow Sn2. It all depends on how big the charge on the carbon is on the secondary halogenoalkanes. So it depends on the groups that are attached. The carbon chain, like if you have a bigger carbon chain, there's more electron donating effect. If you have a smaller carbon chain, there's less electron donating effect. So secondary halogenoalkanes are kind of in the middle. So each molecule, but it's going to depend. It's going to vary. It depends on temperature as well. So Ethan, is this clear? You can't really predict what secondary halogenoalkanes would undergo because there's somewhere in the middle.
So, like, during the exam, will they ask us about secondary alcohols undergoing which mechanism?
I mean, they're not going to. I mean, they've never actually asked so far. But what they can actually ask is maybe they can comment on this charge density. Like they can, I mean, they might give you some information. I mean, they've never actually asked, but that's a possibility. They might ask. So they might talk about the carbocation stability. They might talk about a secondary halogenoalkane, and they will tell you that it has a very stable carbocation. So you would have to guess what type of mechanism would it follow. So if it has a stable carbocation, which means that the carbon positive has a lesser charge density, then it's going to follow Sn1 mechanism. Otherwise, it's going to follow Sn2 mechanism, where the OH minus 1 is going to come in the other way. Remember, it's OH minus 1 would come in, and they're going to push the Cl away. So that's the difference. So they might give you some information about the secondary halogen. Ethan, is that clear?
Yeah, clear. Thank you.
But so far they've never actually asked. Now, moving to the next one. So here's this molecule. You have NH2NH, whatever the molecule. What is this molecule? Can anyone guess what this molecule is? Actually, they've actually told you. I didn't read the other part. It's 2,4-DNPH. And what was 2,4-DNPH? It was a test for aldehydes and ketones. It was a test for serial bond O, carbonyl group, and only serial bond O. I mean, it's not a test for esters or carboxylic acids, aldehyde or ketones. Many but not all organic reactions need to be heated before reaction occurs. When reaction occurs at a good, which reaction occurs? I don't know why they gave this. Why did they give this? Which reaction occurs at a good rate at room temperature 20 centigrade? So I mean, this reaction did not require any heating. I mean, this is the 2,4-DNPH test for aldehydes and ketones. I mean, this is a ketone. So, and this is the reaction that happened. I drew this reaction in the notes as well. Let me just quickly find this. I think we did it in this, on this board. Just one second. Let me label the board as well. Just okay, so maybe in this board right at the end, we did aldehydes and ketones, and we did this reaction or not. Maybe we did this over here. It's this reaction. Okay, this is the reaction that they've written. This is C6H5, C6H3, 2 NO2s. Actually, I wrote this was actually H3. Okay, this was 2,4-DNPH. And a ketone is going to react, or an aldehyde is going to react. It's going to be a condensation reaction. A water molecule is going to be produced, and the N and the C are going to end up joining together with a double bond. And that's exactly what's happening. They've just written the structural formula over here. That you have it's C6H3 and NO2 twice, and there's this ketone, a carbon serial bond O with 2 CH3s attached to it. And this is exactly what's going to happen. So this happens at a good rate. You don't need anything. You just add 2,4-DNPH and you get an orange precipitate. So it was a test for carbonyl groups. The other ones, you need heating. What's the first one? That's your cracking reaction. Now, cracking happens at a very high temperature. Around temperature should be greater than 450, and you would need a catalyst like Al2O3 and SiO2. So what's this other reaction? This is the substitution reaction of halogenoalkanes, which we just did, Sn1 and Sn2, where and all of them they require heating or reflux. Like if you want to get NH3 substituted instead of the halogen, it's going to be ethanolic NH3 plus reflux, or NH3 gas heat in a sealed tube. So that requires heating. And the last one is the reaction with KBr, where the alcohol turns into KOH. That also requires heating as well with KBr. Next is the only reaction is this carbonyl group reaction. Now, next says carboxylic acid P has no possible chain isomers. It reacts with an alcohol Q that has only one positional isomer. What could be the ester formed from a reaction between P and Q? So carboxylic acid P, I mean, this is going to be a very time-consuming question. Carboxylic P has no possible chain isomers. What does that mean? How many carbons would this carboxylic acid have? Like, there's no possibility of chain isomers.
3.
It could have 3. Like, if you have 3 carbon atoms in a carboxylic acid, can there be chain isomers? You can't make branches out of it. Okay? But there could also be 2. Even if you have 2 carbon atoms, there's no possibility of, or it could be 1. Not 4, because when you have 4 carbon atoms, then there's a possibility that you could make, you could rearrange the chain. Like you could have 3 carbon atoms, and there could be a carbon chain branch. So with 4, you get these chain isomers. Actually, this is an important point that you should actually note down as well. Like if you keep carbons under 3, you don't get chain isomers. Now, the question is, it reacts with an alcohol Q that has only one positional isomer. So now think of an alcohol that has only one positional isomers. Now, how many carbons would that have?
3.
4.
Four where there would be positional isomers. Like the OH could be at the end, the OH could be on the second carbon atom. So you're going to get positional isomers with 4.
Sir, 2.
The problem would be you wouldn't have any positional isomers. But
Then it's 3.
3. When a 2 you can't, if you put an OH over here and changing the position, it's going to be the same thing. 1 you're not going to get position isomers. So the only possibility is, अच्छा उसके अंदर मैंने 4 को reject कर दिया. He's saying there is one positional isomer. It's going to be propanol and it's going to be butanol as well, because the OH could either be at the end or the OH could be on the middle carbon atom. Achha, same with 4 carbon atoms. I rejected 4. 4 was, that was wrong. The OH could be at the end. That's one. And one other positional isomer could be. No, actually, let me just sort of understand the question. Just 1 second. The question basically, let's try and understand this statement again. That alcohol Q has only one position isomer. That means it has no isomers. What does one position isomer mean? Does it mean it has 2 isomers or does it mean it only has 1?
Sir, if they've mentioned the term isomer, that means ke ek to hoga. It's not gonna be the original molecule because then there would be no isomers.
No, it means there's just going to be one. But for example, if you look at propanol, propanol is going to have, this is going to be 1 isomer. That's the first one. And then there's going to be a second isomer, positional isomer. So there are 2 positional isomers. He's saying the molecule is just going to have 1 positional isomer. This is basically 2 positional isomers. So what he means is, and he's using a single word. That means, I said, remember, there is no original molecule. There's this isomer and there's this isomer. So that's basically 2 isomers. What he means is there's just going to be exactly one isomer. Okay, so I think, this statement should have been clearer. But what I'm suspecting is that he's talking about either ethanol. What he means is that there isn't any other positional isomer. There's just one positional isomer. That's it. So, for example, ethanol, that's the only possibility. There's no other, there's no second positional isomer. I mean, that this is the only one. Or it could be methanol. Methanol also has just one positional isomer. That's the only place you can put it. So it's going to be one of these two. Is this point clear?
Yes, sir.
Yes, sir.
I said the other thing. Why did I rub this? I said now what could be the ester formed from a reaction between P and Q? So it's either ethanol or methanol.
B.
So it's the only possibility is B. Okay, we did consider butanoate. No, but it can't be butanoate. Because the carboxylic acid P, I mean this is the carboxylic acid side. And the alkyl side comes from the alcohol side, right? So the question was that the carboxylic acid should have no possible chain isomers. So you can't go to 4 carbon atoms. That's going to result in chain isomers. So it was either 3 carbon atoms, 2 carbon atoms, or 1 carbon atoms. So it would either be, it's either going to be propanoate, 3 carbon atoms, they're not going to have chain isomers, or it's going to be ethanoate. So it's one of these three.
Sir,
As
but
a-
then we also said that alcohol, we're not considering butyl for alcohol, right?
I mean, the whole thing is the problem is with this interpretation. I mean, let's rub this. The whole
Sir, it
problem
is
was
either going to be B or D because we need to consider ethyl and propyl.
you can't consider propyl. Problem is with interpreting this statement. It has only one positional isomer. That means I said that there is an alcohol Q and it has only one positional. So there is another one. So I think this statement meant that the molecule is actually there are actually two isomers. There's an alcohol Q and there's one other positional isomer. So I think our first understanding was actually correct for this. That it's either going to be propanol. It's either going to be propanol because it's going to have, like if this is alcohol Q, then it's going to have one other positional isomer, which means that the OH would be on the second carbon atom. Or it's going to be butanol. That if this is Q, then there's going to be one other positional isomer, which is going to be the OH on the second carbon atom. It can't be pentanol because you're going to get more than one positional isomer. So I think we misinterpreted this particular statement. So it's either going to be propanol. I think we did misinterpret this. Okay, there was alcohol Q.
Sir,
Yes.
isn't like the primary alcohol not an isomer?
Wait once. What do you mean primary alcohol is not an isomer?
Is it like it's just an isomer would like change if it changes chain, right?
Yeah.
So if it's in the original first chain,
See,
it's not.
let's say this is a primary alcohol, right? The point is what you're basically, I think what you're confusing this with is that the isomer could be, you could have many different isomers. Like you don't even need the OH to be an isomer. Like you can get rid of the OH altogether. You can have a molecule where there's an O in the middle and that would still be an isomer. Ethan, do you get the point?
Yep.
So you can come up with many different isomers. What he was basically talking about was a positional isomer. And what we were getting confused was that there was an alcohol Q and it has only one positional isomer. What we were getting confused was whether there is exactly just, the molecule, there's only one molecule that can not form any other isomer, and that's the only positional isomer, or is there an alcohol Q and that alkyl Q has another isomer which is a positional isomer? So I think that is what he meant, that there were actually two versions of the molecule, that there was an alcohol Q and that alkyl Q then had another positional isomer. So the OH could be on some other carbon atom. So these were the only two possibilities. Is this point clear? Hiba, Rida, is this point clear? To everyone, Mohammed, is this clear?
Yes.
Minahil, clear hai?
Yes, sir.
Acha, so I think this part was the one that we got wrong. Acha, over here we got this right in the first that there was a carboxylic acid P and it has no positional possible chain isomers. So the carboxylic acid was either going to have 3 carbon atoms or 2 carbon atoms or 1 carbon atom. The OH side comes from the carboxylic acid. So it's either going to have 3 carbon atoms or it's going to have 2 carbon atoms because it's not going to have any chain isomers. If you go more than 3 carbon atoms, you start forming chain isomers. So it was either A or C. And we figured out that the alcohol could be butanol. So it's going to be, the answer is going to be A. It can't be pentanol. This side comes from the alcohol side. It can't be pentanol because pentanol is going to have a lot of positional isomers. Like if you have 5 carbon atoms in an alcohol, then the OH could be on the, let's say this is Q, then it's not going to have one other positional isomer. The OH could be on this one, the OH could be over here as well. So there are actually 2 positional isomers of pentanol. So it can't be pent. That is the part that would be wrong. The carboxylic acid can't be greater than 4 or 4. So A was the correct answer. Is this point clear? Is this question clear to everyone? Bazgar?
Yes, sir.
Yes.
ठीक है.
Yes.
ठीक है. So I think we got this interpretation wrong. And the next one. And remember, isomer questions are probably one of the toughest. ठीक है. You have to. Whenever you see isomer questions, skip them. ठीक है. Keep them at the end. They're just going to waste a lot of your time. Now, which compound is chiral and reacts with Na2CO3 to give CO2? So carbonates, they react with carboxylic acid. So that's an easy one. So you have this one is a carboxylic acid, the last one, and this one is a carboxylic acid. These two are not carboxylic acid. This is also not a carboxylic acid. It's an ester molecule because it's HC. Then there's 2 oxygens, so that's double bond O and O. Then there's another C, and then there's H, and then there are 2 branches, right? So not a carboxylic acid. So you have to choose between A and B. And he's looking for a chiral carbon. Any carbon that forms double bond, that's not chiral. In carboxylic acid, the carbon is forming a double bond. It's C double bond O and OH. So that's also not chiral. So any carbon with double bonds is not chiral. The only possibility is then this one, that there's a C, H. It also has a Br, and it also has a carboxylic acid group, C double bond O and OH. And at the bottom there is CH2 and there is CH3. So this carbon atom is chiral. Okay, is this clear?
Yes, sir.
Yes.
So which compound when hydrolyzed gives propanoic acid and propan-2-ol? They're all esters. So looking for propanoic acid and propan-2-ol. So which molecule could it be?
It has to be मतलब B or C क्योंकि it has to be 6 carbon atoms. So
it has to be 6 carbon atoms, but around the double bond O, there would be 3 carbon atoms on one side and 3 carbon atoms on the other side, right? Like if I look around the oxygen, it's propanoic acid and propanol, right? So this is incorrect because on this side there are 4 carbon atoms. So I'm going to eliminate most of I'm going to eliminate the wrong ones. This is also wrong. There are 4 carbon atoms on this side, so that's not possible. This one is incorrect. There are 2 carbon atoms on one side, so by default the answer is C without even solving the question. Is that clear?
Yes.
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 So alcohol and carboxylic acid. So we didn't even need to solve the questions. You would get. These are the questions that you're going to save time on.
Sir,
Yes.
didn't you say we need to have 3 carbons on each side?
So there are 3 carbon atoms. Like oxygen, around the oxygen, this side there are 1, 2, 3 carbon
Around the
atoms.
oxygen. Okay.
Okay. And we can draw this molecule as well, just for the sake of practice. Propanoic acid is acetyl bond O and OH. I said, remember, forget the hydrogens. Whenever you're trying to do this quickly, don't draw the hydrogens. The other one is propan 2-ol. So that means that the OH is on this middle carbon atom. So you have to draw this vertically so that the OH are pointing towards each other. The OH and H would be lost. That's going to form water and they're going to connect. So it's going to be, if I write the condensed formula, it's going to be CH3. Then there's CH2. Then there is CO followed by another O. And then there is this one will have CH. And it will have two branches attached to it. So there's a CH3 branch, another CH3. So hence it's going to be C. Now section B, an isolated gaseous atom of X as, and remember, save time on this. Remember, if the first one is incorrect, then 2, 3 is automatically correct. And if the second one is incorrect, then the only option left is D. Okay, always save time. An isolated gaseous atom of X has paired electrons in at least one of its 3D orbitals and has a filled 4s subshell. What could be the identity of X? Paired electrons in at least one of its 3D orbitals. What does that mean? How many electrons do you need in 3D? If you need a paired electron in at least one.
6.
Okay, so you need 6. Okay, if you do 5, that's D has 5 orbitals, D subshell. And if any number lower than 5, that means electrons are always filled in a single manner first, and each orbital is going to just have one electron. So it has to be 6 or greater than 6. So let's start with copper. Copper is 29. Copper is, remember, argon is, for transition metals, remember, argon is 18, and followed by 18 would be up to, and then followed by 4s2 and 3D.
Yeah.
And 4s gets filled first. So all transition metals, the top ones, they usually have this electronic configuration. It's argon, 18 electrons, and then fill the rest of them. So that's 29. So you need to fill 2 electrons here and 9 over here. So that's 11 more. But copper is your special case. The 4s is just going to have 1 electron. The 3D would actually be full. And किसी का mic on है किसी का. अच्छा, so you have 4s1 and you have 3d10. He had specifically said that the 4s should be filled. For copper, it's not filled. And remember, copper was your special case. I mean, there were some exceptions, and copper was one of them. Then you have iron. In iron, it's 26 electrons, so it's argon, which is 18. And then it's 3d and 4s. So 2 electrons go to 4s, and then there would be 6. So after 18 electrons, it's that's your electronic configuration, and that's going to be correct. And then look at gallium. Can you even check what gallium is? As gallium is over here, it's 31. Now, when you reach 31, that means these are all full. Like you would have argon 18 electrons, and then you would have 4s2 and then 3d10. That's 30 electrons. So these are all full. And then 1 electron in some other orbital, right? Whatever comes after 4s. Probably 4p. So 1 electron goes to 4p. So 3d would be paired and the 4s would be paired as well. So 2 is also correct. Next one is, which allotropes of carbon have a giant molecular structures? And that's going to be diamond and graphite. Buckminster fullerene does not have a giant covalent structure. Remember, I told you we did some introduction of this, which was that that you have graphite, you make graphene out of it, you get fullerenes. Let me just. So these are the structures that you have for carbon. One second, let me. So these ones. Now, graphite is the sheets of hexagonal carbon atoms. Carbon is making 3 bonds and 1 electron is delocalized. So it's a sheet that can conduct electricity. And there would be sheets, layered structure. There would be a stack of sheets, millions of sheets all stacked on top of one another. That's graphite. And there would be weak van der Waals forces, which would make the graphite structure very weak, very soft. The layers can easily slip and slide because the van der Waals forces are kind of weak. Then, if you isolate a sheet, a single sheet of graphite, that's known as graphene. That's probably one of the strongest known substances according to its in terms of its relative to its mass or relative to its size. So graphene sheets are very good conductors of electricity. Plus, they're flexible. Graphite is not flexible. TK, I told you that if pages are stacked in a copy, you can't really bend or fold those pages. But if you take one page out, you can sort of make lots of structures out of them. So there, you can make carbon nanotubes. You can make fullerenes, this is your Buckminster fullerene. Carbon nanotubes can also be very giant sized. I mean, it's the giant sheets of graphite rolled into a tube-like structure, and they could have very large lengths. So they are also giant structures. Diamond is obviously a giant structure. Fullerenes are the ones that are not giant structures. They have a very specific number of carbon atoms. Sometimes they have 60 carbon atoms. I mean, there would be some images over here. This one, for example. So it's the same graphite sheet rolled into a ball-like structure. So you have C60. This is known as a buckyball. This is known as a Buckminster fullerene. You have C70, C50. So a number of different fullerenes actually exist. So a number of different fullerenes exist, but they are not giant structures. They have a very limited number of atoms in their structure. TK, is this clear? Mohammed,
Yes, sir.
Rizal, Hiba, is this clear? I said now, the next thing is number 33. Which statement about endothermic reactions are correct? On the reaction pathway diagram, the products of the reaction are lower than the reactants, which is incorrect, because in endothermic reaction, the reactants, they gain energy. So the products are on the reaction pathway diagram higher than the reactants. So the first one is incorrect, which means the second 2 and 3 are correct. Just make sure that the first one is incorrect.
Sir, is this a formula? If the first one is incorrect, the last two has to be correct.
No, because this is the marking key, right?
Ji.
So if the first one is incorrect,
Hmm.
so A, B, and D are now out of the question. The only option left is C. So if the first is correct, just mark C. And if the second is correct, then it's going to be D.
अच्छा
मतलब
हर जी ठीक.
Unless, I mean, this works unless they change this. I mean, they're not. I don't think they're changing this right now. I mean, just make sure that you have the same options. It's always the same key. It's always the same key. So this always works. One incorrect. No need to wait. I mean, because time is very important in an MCQ paper. So if 2 is incorrect, don't bother checking the other ones. I mean, if you're sure that number 2 is incorrect, and if you're sure that number 1 is incorrect, only check the other ones if you're not sure about 1 as well. So now next, this one. The rate of chemical reactions can be increased by the addition of a suitable catalyst. For which reaction can a heterogeneous catalyst be used? Heterogeneous catalyst is a catalyst that has a different state compared to the reactants. So in the Haber process, it's iron, and it is a heterogeneous catalyst because it is a solid, and the other two are all the reactants and products are gases. So that is a different state. I say in the second one, this is V2O5, vanadium pentoxide. That's the contact process. and that's also a solid. So that's that also has a different state compared to, because all the reactants are gases. Uh, in this one, this is actually, where do you see reaction number 3? Does anyone remember what reaction number 3 is?
Yes, this is for a
Uh,
catalyst.
combustion
The
engines.
exhaust
ठीक है,
fumes.
Exactly.
ठीक है, exhaust fumes, and you have a platinum or a palladium catalyst. That's also a solid. It's like a honeycomb structure in your exhaust, car exhaust, that turns the harmful oxides of nitrogen and carbon monoxide, which are poisonous, into less harmful products. So that's your catalytic converter. Just a second. Now, next one is, which chlorides when added to water can produce a solution with a pH of less than 5? So this is all about hydrolysis of chlorides. We actually
So what
did.
was the correct answer in the above question?
It's going to be A. All of them are correct.
Okay, all of them. Sorry.
Okay, so all of them are correct. Now, next one is, which chlorides when added to water can produce a solution of pH less than 5? So I'm just going to open the inorganic worksheet. Where did TK, I think yesterday we just reached this part where we were talking about the chlorides. We actually didn't start this. Chlorides with water, TK. So he was talking about MgCl2, and AlCl3 and SiCl4. Now MgCl2 doesn't really strongly hydrolyze. It produces a pH of 6.5. AlCl3 hydrolyzes pretty strongly and produces AlOH3 and HCl. And the same happens with SiCl4. It also mixes with water and produces this. Now I'm just going to go into a bit more detail, maybe do this and explain this over here. What was he saying? That produces solution of pH less than 5. MgCl2 is not going to do that. These two are going to do that. Uh, MgCl2 has a weak hydrolysis, a very weak hydrolysis. It usually just dissolves. So I'm just going to explain this a bit. That what's happening here. Now what's happening in hydrolysis is, let's start with NaCl. Let's start with NaCl. NaCl, if you dissolve NaCl, it simply dissolves in water. It forms Na+1, which is aqueous, and it produces Cl-1, which is also aqueous. No hydrolysis or no reaction happens. Why does it not happen? What happens is that this Na+1 is going to start attracting, when you put it in water. Water is a polar molecule, and polar molecules, they get attracted to Na+1 because it's a positive ion. So from all sides, here just going into a bit more detail. So from all sides, water molecules, they get attracted, right? And water is a polar molecule. The H is positive, and the O has lone pairs, and these lone pairs are going to be attracted to the positive ion, right? So imagine from all sides, water molecules getting attracted to sodium ions, and sticking to the sodium ions. So that is what happens. A complex is formed. And let me just show it's a. You get probably something like this. This looks like a good decent image. So the sodium ions are kind of, all the water molecules are kind of sticking to it. The H are pointing away. I mean, they're not sticking to the positive ion. The negative oxygen is the one that's basically sticking to the water molecule. So that's what's happening. Now, moving to the other ones, what happens with, let's say, AlCl3? It also, the first step is, now the major difference is Al is 3 plus. Okay, what that means is that the positive charge is really, really strong. So now imagine a water molecule that's getting attracted to the Al3 plus. The lone pairs, the negative oxygen is going to be very strongly attracted to the positive ion. What's going to happen to the H positive? It's going to be very strongly repelled, or it's going to be pushed away. And the end result is that the H kind of is knocked out, and an H positive ion is formed. So what happens is that your complex that was formed, where Al was surrounded by 6 water molecules, and this is called a complex ion. Although this is not in your course yet, it's in A2, but this specifically want this equation. So this water molecule, what happens is that the water molecules, they start breaking up into OH hydroxides. Okay, so there's OH minus 1 that's left. So 3 of the water molecules, they break down into OH ions, and 3 H plus 1 ions are produced. Is this point clear?
Yes, sir.
Okay, is this point clear to everyone? Ethan, Mohammed, Rida, Heba, Mazga, is this clear?
Yeah, clear.
Yes.
So why didn't Na plus 1 do this? Because Na plus 1 did not have a very strong positive charge. So it wasn't really repelling the H positive that strongly, so that the water molecule would break down. But aluminium ions are doing that very strongly, which is why you're going to get a very acidic solution, because aluminium ions, when they enter water, when they dissolve in water, so AlCl3, basically what the equation that they expect for you is this one, that AlCl3 first dissolves and forms or dissociates, and then it starts to hydrolyze, that the aluminium ions with 6 water molecules, which is basically this one, the second equation. Okay, no need to write it again. As Mg is in the middle, Mg would do this, but not very strongly. So not a lot of H plus 1 ions are going to be produced with Mg. So if you have Mg2 plus, the H plus 1 would get knocked out, but not a lot of them, because it's not a very, it's also not a very strong positive charge. So one second, where did our notes go? This one. So remember, strongly acidic, SiCl4, AlCl3, that's strongly acidic. MgCl2, very weak hydrolysis. Not a lot of H plus 1 ions are going to be produced. It's just going to be pH 6.5 or 6.6. Very few H plus 1 ions are going to be produced. Remember, very slight hydrolysis, or almost no hydrolysis. NaCl, absolutely no hydrolysis. It simply dissolves. So when we go back to the question, it's going to be, it's not going to be MgCl2, it's going to be weak hydrolysis. The first two are going to be strongly acidic. Okay? Is this clear to everyone?
Yes, sir.
I said then, next one, acid rain continues to be a problem. A statement about acid rain are correct. Acid rain is formed when oxides of nitrogen or oxides of sulfur react with water in the atmosphere. Acid rain causes it. So is the first statement correct? That oxides of nitrogen and sulfur react with water. That's definitely correct. That is what acid rain is. Acid rain causes an increase in the concentration of heavy metal ions in water courses. That's definitely not correct. I mean, there are no heavy metals in acid rain. And this one, So I'm going to talk about 2 again because there's a problem now. Because if you look at number 3, nitrogen dioxide will catalyze the formation of SO2 to SO3, which is also correct. So we have to actually look into 2. There must be something wrong with 2. Nitrogen dioxide will catalyze. It does catalyze. What it does is that SO2, it acts as an oxidizing agent. It acts as a catalyst. It turns it into SO3, and NO is formed. And that NO again by itself oxidizes in air and turns back into NO2. So this is it is acting as a catalyst. So the third statement is correct. Can anyone tell me how could 2 be correct? Because acid rain is basically H2SO4 and HNO3.
Sir, it basically corrodes the surface soil layer, na? So वहाँ से it can carry the
Basically,
metal.
it's an acid, right? What do acids do? They react with
Reacts with the metal.
they react with metal, and they pretty much react with any types of metals. So that's probably why option 2 is going to be. I mean, you have to check this one, but that's the reason for option 2 has to be. I mean, because 1 and 3 are correct. Now you don't have any options where 1 and 3 are correct and 2 is wrong, because if you look at the key, there's no option where 1 and 3 are correct. So you have to really try and understand what 2 is all about. So that's where you're getting metal ions in water courses, because acid rains are dissolving metals. They react with metals. Next one, which compounds contain a chiral center? So you have to draw the molecules. Butanoic acid, it's 4 carbon atoms, and it's 2-hydroxy, which means it's OH on the second carbon atom. Is this chiral? There's going to be 1 H here.
Yes.
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 Then there is 3-hydroxy. I didn't draw butanoic acid. Then there's, I mean, this was 2-hydroxybutanoic acid. Butanoic acid would be on this side. Then 3-hydroxybutanoic acid. Butanoic acid is double bond O and OH. And now it's 3-hydroxy. So OH is on the third carbon atom. Remember, carboxylic acid side is always carbon number 1. So this is also chiral, right? So that's also correct. 4-hydroxy, that's definitely not chiral. Or is it? So butanoic acid and OH on the last carbon atom, the fourth one. These are all the hydrogen atoms. So is there any chiral carbon in the third one? Each
No.
carbon is bonded to 2 hydrogens, so there is no chiral carbon atom. As the next one is diagram shows the monomer used to make PVC, assuming that one particular molecule of the polymer forms from n molecules of the monomer. Which statement are correct? I mean, the polymer would look something like this, that the same repeat unit would be, this chain would continue over and over again. So the relative molecular mass of this polymer molecule is approximately 62.5 into n. What's the mass of this thing? Is this 62.5? 2 carbons, that 24 plus 35.5 plus 3 hydrogens.
Yes, it is.
So it's going to be 62.5 times n, because remember, in addition polymerization, things are just getting added. There is no molecule being added or no molecule being removed. Okay? In addition polymers, the mass of the polymer is just a multiple of the monomer. Unlike condensation polymers are not in your course yet. That's in A2. But if you remember O-levels condensation polymerization, a water molecule was produced. That would lead to a decrease in mass. But in addition polymers, things are just getting added up. There's nothing getting removed or eliminated or getting added. So it's going to be 62.5 n. I said there are n chiral carbon atoms in this polymer. So is this carbon atom chiral?
Yes.
It is going to be chiral because the top is different, the bottom is different, the right side chain is going to be different because it's going to have a different length. The left side chain would also be probably different, and it's going to have a different length. So there are n chiral carbon atoms in this polymer molecule. I mean, that's going to be correct because each one has n chiral carbon atoms. So in total, they're going to be n chiral carbons. Then you have there are 5 n sigma bonds in one polymer molecule. That's how many sigma bonds are there in this molecule?
5.
That's 1.
6.
That's 2, 3, 4, and 5. I mean, 5 is up till here, right? But if you count these, then that's 6 and 7. I mean, you have to count the side ones as well. So I think this last statement looks incorrect. Is this clear? Ibrahim, is this clear?
Yes, but matlab, are we supposed to count that or not? Matlab, are we supposed to count those atoms?
Because he's talking about the whole polymer molecule, no? I mean, the whole polymer molecule is not just these 5. I mean, this is 5 sigma bonds, right? This is another 5 sigma bonds, right? But what about the sigma bonds that are formed between them? I mean, you're not counting them. So it's not going to be 5 n sigma bonds. I mean, you have to count the ones that are in between as well. Mohammed Ethan, is this clear? Rida, is this clear?
Yep.
Hiba?
Yes.
Okay, next one. An organic compound X has the following skeletal formula. Which statement it's a primary alcohol? Is it a primary alcohol?
Yes.
Okay, this carbon atom is it has 2 hydrogens, so it's definitely a primary alcohol. What about the next one? X will dehydrate to give an alkene. Is that correct?
No.
Why not correct?
It is,
I mean,
right?
I mean, there's an H, so the OH would be lost from this carbon atom, and H would be lost from this carbon atom, and there's going to be a double bond formed over here. So it will form an alkene. I mean, the only way it can not form an alkene is that if you remove the OH and there is no hydrogen atom on the neighboring carbon atom, then an alkene would not be possible. As long as there is a hydrogen atom next door, then an alkene will be possible. As an X will
Sir,
undergo, yeah.
if this was a secondary alcohol, would there be more than one alkene produced?
Like it's not secondary alcohol. It has to be a very specific type of secondary alcohol, because secondary alcohol is a very general statement. There are lots of molecules that are secondary alcohols. For example, like this is a secondary alcohol, right? So and what happens if you remove the double bond and the H is lost over here? A double bond would form here, right?
Yes.
But it won't form cis and trans isomers. So just 1 minute break. Okay, so let's continue. Ethan, so what was your question?
It was Sohail.
Yeah.
I didn't hear that. Can you repeat?
Oh, it was
Oh,
Sohail's question.
So what was the question?
I told that if it's a secondary alcohol, is it possible that there's more than one type of alkene produced?
I mean, you always have to check. I mean, that was what I was answering. You always have to check. And remember when I told you that because the OH could be lost, the H could be lost from the right side, or it could be lost from the left side, right? So you have to check every time, and also look for cis and trans isomers because they're going to be treated as different molecules. Is that correct, Sohail?
Yes.
Is it,
Sir, what do you mean by the cis and trans molecules being treated differently?
I mean, for example, it's this molecule, right? Okay, there is. So, for example, there is OH being removed from this carbon atom, and H is lost from the neighboring carbon atom. Okay, double bond forms over here. There could be another molecule, another alkene that could be formed, where the OH could be lost and the H could be lost from the carbon on the left, right? And the double bond would be formed over here. What would happen in this case? If you look at the molecule, it has a double bond in the middle, and there's a carbon chain. And the carbon chain, this one will have 1H probably. This will also have 1H, 3Hs, and 3Hs. Now, this is the alkene that's being formed. For this alkene, it's going to be in two forms. There's going to be a cis version and there's going to be a trans version. Like if you draw the alkene, it's going to have like the three-dimensional structure. There's going to be a cis version and a trans version. Or it could be the other way around, that the H and CH3, the H over here is pointing down and the CH3 is pointing upwards. So this molecule would actually exist in two forms, two stereoisomers. Is this clear?
Yes, sir.
So X will undergo a substitution reaction with chloride. Will it? It will undergo a substitution reaction with chloride ions. Like Cl ions, they do substitute OH. So that's also a possible. I mean, that's true as well. Alcohols can be converted into halogenoalkanes. Next one is 2,2,4-trimethyl pentanol is used in the manufacture of adhesives. Which reagents will it react with? Pentanol. Its pent is 5 carbon atoms. Al means it's an aldehyde. 2,2,4-trimethyl. That means 3-methyl. 2. This is 2. And then there's another 2. And then there is 4. So that's 2,2,4-trimethyl. So that's all of this is a CH3. This will have this is a CH2. 1H here, 3 H's here. So this is 2,2,4-trimethyl pentanol. It's going to react with 2,4-DNPs. That's a test for carbonyl. It's going to react with aldehydes because aldehydes, they do get oxidized to carboxylic acids. And it's not going to react with the iodoform test is not going to happen because the iodoform test is for CH3 with a C double bond O next to it. I mean, it has to be this structure that should be present over here. Like a methyl should be present right next to the carbonyl group, which there isn't. I mean, this structure is not here. It's not present over here. So that's not possible in this particular case. Is this clear as well? Remember, alkaline aqueous iodine, the iodoform test. It's a very specific test for a very specific structure. So it's either this structure that needs to be present, this exact. I mean, it's a positive test for both these structures. you get a yellow precipitate. What happens is that the molecule breaks over here. This forms CHI3, which is a yellow precipitate. It's known as triiodomethane. And this other side turns into a carboxylic acid. I mean, whatever this other side is, it just turns into a carboxylic acid. It would be RC double bond O and OH. This would also be RC double bond O and OH. And since alkaline conditioners are used, you're not going to get a carboxylic acid. You'll get a salt of the carboxylic acid. So there's not going to be any iodoform test. That's not going to happen here. ठीक है, is this clear as well?
Yes, sir.
So ठीक है, we'll continue this. Continue with another paper next time then. ठीक है, we're done with this one. So let's continue next time. Okay then.
Thank you.
Okay, then Allah Hafiz, sir. Thank you.
Take care. Allah Hafiz.
Thank you.
Sir,
जी.
can you like give me some guidance regarding how to prepare for the coming AS level exams? I'm going to appear for them and matlab jitna time रह गया है, like less than 2 months. So can you give me like some advice regarding that?
एक second रुकना जरा. I say what you can do is कि अभी you've done the whole पूरा कर लिया आपने वो सारा syllabus.
Yes, sir.
अच्छा, the main advice is कि I mean the syllabus for AS मतलब O levels and A levels की ना तैयारी जो है ना वो different है, ठीक है. A levels के अंदर you focus less on the syllabus because it's the questions that are more difficult, ठीक है. तो आप reverse में पढ़ो. बताओ आप क्या करो कि आप ना पेपर अटेम्प्ट करो, ठीक है. फॉर एग्जाम्पल ये क्वेश्चन है ना, और रिवर्स में पढ़ना है, ठीक है, कि आपने पेपर अटेम्प्ट करना, इवन लेट्स से यू नॉट प्रिपेयर्ड, ठीक है. पेपर अटेम्प्ट करो एंड लेट्स यू गॉट दिस क्वेश्चन रॉन्ग, यू डिडंट अंडरस्टैंड दिस क्वेश्चन, राइट. तो आप उस पर पॉइंट बना लो कि उस पेपर को थोड़ा सा एनालाइज कर लो कि जी ये टॉपिक्स हैं मैंने रिवाइज करने हैं. फॉर एग्जाम्पल इसमें यू कुडंट फिगर आउट कि जी ये मॉलिक्यूल की नेमिंग किस तरह है, ठीक है. attempt a paper, identify your weak areas कि ये क्वेश्चन मुझे समझ नहीं आया. Then study and उस मतलब जब पेपर अटेम्प्ट करो, लेट्स से आपने 40 क्वेश्चंस MCQs अटेम्प्ट किए हैं, ठीक है, और लेट्स से you were only able to answer 20 of them and you couldn't figure out the 20 other questions, right? क्योंकि टाइम लिमिटेड है, जो चीज आती है ना उसके ऊपर टाइम नहीं जाया करना. तो आप बस वो अगर एक पेपर आपने अटेम्प्ट किया ना 40 MCQs का and you've identified कि ये 20 क्वेश्चन तो मुझे समझ ही नहीं आया कि क्या है ये. Focus on those 20 questions. उसके लिए पढ़ो, उसके लिए बुक खोलो, उसके लिए नोट्स खोलो, उसके लिए टीचर से कंसल्ट करो, ट्राई एंड आंसर. अब वो जब 20 क्वेश्चंस आंसर अंडरस्टैंड कर लोगे ना तो आपकी बहुत सारी तैयारी हो जाएगी. वो सारी चीजें जो आपको नहीं आती थी ना वो थोड़ी बहुत अब आपकी उसमें चीजें इंप्रूव हो जाएंगी. फिर आप अगले पेपर में मूव करो, उसके अंदर हो सकता है कि यू आंसर 25 क्वेश्चंस. तो आपने बड़ा फोकस करके ना द थिंग्स दैट यू आर गेटिंग रॉन्ग उनको प्रिपेयर करो, उनके लिए स्टडी करो. और व्हेन यू डू दिस फॉर एवरी पेपर तो प्रीटी मच आपका टाइम भी वेस्ट नहीं होगा, क्योंकि वैसे आप रैंडमली अगर बुक खोलोगे ना. आर यू गेटिंग दिस?
Yes, sir. Yes.
अगर आप वैसे, क्योंकि दो मोड्स है ना कि या तो आप एक बुक खोलो और बुक में ना आप बैठ के ना वो पढ़ना शुरू कर दो जो सिलेबस है आपका, कि आपने एटॉमिक स्ट्रक्चर आप कहते हो मैंने एटॉमिक स्ट्रक्चर आज रिवाइज करना है. अब बहुत सारी चीजें एटॉमिक स्ट्रक्चर की आपको वैसी आती होंगी, मतलब डोंट वेस्ट टाइम के एटॉमिक्स, मतलब जो चीजें आती हैं उसके ऊपर तो आप टाइम ना वेस्ट करो. आप सीधा डायरेक्ट पेपर अटेम्प्ट करो, बेशक आपने कोई प्रिपरेशन नहीं की हुई, और उस पेपर में जो जो चीजें आपको नहीं आती ना वो सारी आप पहले पेपर में बड़ा टाइम लगेगा, मतलब पेपर आप अटेम्प्ट कर लो और फिर उस पेपर के क्वेश्चंस को अंडरस्टैंड करने के लिए स्टडी करो. उससे होगा कि आपकी स्टडी ना बड़ी फोकस्ड होगी. इट्स गोइंग टू हिट ऑल दोस एरियाज जहां पे ना जो आपको नहीं आते. अगला जब पेपर अटेम्प्ट करोगे ना आपकी कंडीशन बहुत बेहतर होगी, ठीक है. तो ये थोड़ा सा ना रिवर्स में पढ़ो, पेपर पहले अटेम्प्ट करो और फिर उस पेपर के जो क्वेश्चंस नहीं आते ना उनको सॉल्व करें. और रिमेम्बर कि हेल्प चाहिए होगी, टीचर से हेल्प, अपने दोस्तों से हेल्प, मतलब किसी ग्रुप से हेल्प. You need help in solving these questions and understanding these questions somewhere. तो वो जरूर कंसल्ट करना, ठीक है.
Okay, sir. Thank you.
चलो ठीक है, ओके, टेक केयर.
Allah Hafiz.
हाफिज.